Hey folks, this is Nathan Jones here to talk to you about the power of a lookup table. What is a lookup table? Well, here's a quick example. Let's say I wanted to compute the sine of a number from 0 degrees to 359 degrees. I could call into the library sine function, which might take a bit of time because that can be computationally intensive, or I could create an array of 360 elements where each element in that array corresponds to the sine of that value in degrees. And then looking up the sine of 4 degrees is simply an access into memory, into this array. And this has potentially some performance boosts to our program. We can avoid having to compute the sine function on the fly. But if we expand our idea of what we can do with arrays, we'll see that this idea of a lookup table can do a lot more for us, right? In addition to making our programs faster, it can help us clean up our conditionals, which can make our program easier to read and easier to change. It can actually start to blur the line between hardware and software. It can give us some runtime configurability or even polymorphic behavior. And it can help us capture our program's knowledge as data, not hard-coded logic. We'll see what that means in a sec. I mean, that's one of the coolest ones, but we'll get there in just a couple of slides. The lookup table and its power is what caused Charles Lohr to say, the single most powerful software technique that I use to do impossible things is lookup tables. It's a powerful statement. And huge shout out to Charles Lohr. His Hackaday Superconference talk, Accomplishing the Impossible with Lookup Tables, is really what kind of inspired me to do a bunch of my research and put together this talk. Okay, so we are going to look at each of these benefits kind of in turn that a lookup table gives us, and I'll share with you a bunch of examples about how a lookup table can give you all these many benefits. So let's start with fast math, going back to this idea of my sine lookup table. So if I have a lookup table like I just described with the sine function where each element is the sine of that index value in degrees, I potentially get some pretty cool performance speed up. In some of my testing, I could run this, or I could access the sine value 7 times faster than I could if I actually computed the sine of what I wanted. In fact, my implementation was actually smaller than the library sine function, which is not typically the case. Usually we are allowing ourselves to take up more memory in order to run faster, but in this case it was a little smaller. And as you might expect, there was just a little bit of error in each number when we were accessing it in an array like this, about 2.5% on average. Now that might seem like a lot, but let me put it in perspective. Let's say that I was using my sine function in order to determine the vertical displacement of an arm, which we'll say it's 30 centimeters, right? So about a foot. On the end of some type of servo motor, right? And it's going from 0 degrees to 90 degrees, and I want to know how far off the ground the end of my arm is. So I'm going to compute that with the sine, and if I am off by 0.0076 maximum, what that means is for a 30 centimeter long arm, my vertical displacement is only ever as inaccurate as about 1/4 centimeter, which honestly for a lot of applications is completely sufficient. And what we'll see as we dig into this is that the lookup tables almost invariably have slightly less accuracy, but as long as I know what level of accuracy I need, then I can try to find the right balance between speed and accuracy. Now, if I'm going to code this lookup table in real life, honestly, what I'm probably going to do is encapsulate it in a function, which you can see right here. And that gives me a couple of different benefits. Primarily, it helps decouple any code from the specific array elements or kind of the initialization of this array. So nothing in my code knows that my sine lookup table is 404 elements long, which is helpful if I ever need to change that in the future. Additionally, this is an example of a lookup table where I have to kind of change my input value a little bit in order to get to the right index. So putting this table access into a function allows me to keep these two elements together. And so I want to point out a couple of the kind of road marks or landmarks, I guess, of this implementation. So these are some things that we'll see in the future in different lookup table implementations. So I've already mentioned number one that this lookup table implementation is function local. Additionally, I'm going to use the const qualifier to try to help my linker store this table into Flash, not RAM. In almost every case, that's what I want because the table is probably not changing and my system probably has more flash than it does have RAM. But occasionally there are times when I might want to put that lookup table in RAM, like if I'm computing values or changing values at runtime. Or maybe I do have more RAM. Now, if I'm putting this lookup table inside the function, I definitely want this static qualifier because I don't want this table like copied into the stack every time I run into my function. This lookup table is an array of doubles because I wanted to, in this case, I wanted to try to match the library sign function signature. It's single dimensional, it has one dimension, but we'll see with lookup tables later on that have multiple dimensions. And this is a table that was computed manually. So I wrote some software to kind of figure out the sign, each value that I wanted to put in my array here. And then I kind of hard coded this in. But if I wanted to, I could have computed my sign function also at runtime or found a different way to kind of embed that into my, my software here. Now, in the previous example of my sign lookup table, I was using my argument as like the index into my array. That's what we might call a direct access, right? Because I'm directly accessing the array. In this case, I'm changing the value first initially, and the reason I did this was because in trying to match the library sign implementation, I wanted to take in a value in radians. But a full one cycle of sign is 2 pi radians, like a little over 6. 6 elements was way too few to put into an array. So I decided that my array was going to be spaced 1/64th of a radian apart. And so that's what gave me the weird number of 404. But it makes accessing the array not that much more complicated, right? I can take my value in radians and multiply by 64 to get like the number, the offset kind of into my array. And then what I do here is a very simple form of rounding to get to the right index or integer value into my array. This addressing method is not direct, so it's one we might call hashed, where I'm effectively kind of permutating my input a little bit to get to the correct array index. And we'll see some more examples of this in the future. It's important also to not forget balance checking on your arrays to make sure that this value doesn't accidentally exceed 403 and try to access memory elements off past the end of the array. Okay, so this is a totally valid sign implementation, but there are a number of ways that we can sort of improve the accuracy or improve the speed. And to be thorough, I wanted to share those with you now. So the first thing we can do is add piecewise linear interpolation. And so on the left side of the picture here, you can see what our previous version of the sign lookup table is doing. We're effectively finding the nearest 1/64th of a radian to whatever our value is and returning that value from my array. But what that means is, if you think of the sign function as being this blue dashed line, there'll be spots where I'm right kind of at that boundary between two array elements, but I sort of round down to 1, and I have this error between the array lookup and my actual function. And I can make that array or that error much smaller if, instead of just looking for the nearest element, I find the nearest 2 elements and then trace a straight line between them and kind of scale my output accordingly. So this app note from Microchip was very helpful for me in order to figure out how to set that up. And you can see an example here of, if we have this element in our lookup table and this element in our lookup table, instead of having the error that would be from going, rounding to one or the other. If this black dot is my input, I can minimize that error significantly by figuring out how far kind of along this line I am and returning like a scaled value. If my lookup table, I'm worried about it being too big, then I can change it into something called a sparse lookup table by taking advantage of spots on my function, like down here where sign crosses the origin, where the function is really linear, and it's only around kind of the maxima and minima where the function changes very quickly. And so if you think about using our linear interpolation to get a value for this lookup table, I can keep the points near the zero crossings spaced much further out and not have to worry about having worse error, and bunching up the points around the spots where my function changes very quickly. So implementing that would require sort of setting up effectively like a key value list, right? Where my keys here are my X values, and then I'm associating those X values with the Y values. And I can create a much smaller table with the same amount of error as if these points were spaced evenly apart. By just taking advantage of spots where this function is fairly linear. Now, what this means is that I don't have necessarily direct access into the array anymore. I kind of have to look for the key that matches my input. But if I'm trying to balance speed with memory size, then this might be a good implementation. Additionally, I can kind of change the data type that's stored in my array. If I just worried about size, but I want to keep my precision, I can switch from a double precision floating point number to a single precision floating point number and kind of cut the size of my lookup table in half. Additionally, I can switch from floating point numbers to just fixed point numbers, which use integer numbers, to represent both integer and fractional portions. So the notation typically is Q something dot something. Q7.8 means I'm taking a 16-bit number and reserving 7 bits for the integer portion, or really 8 because it's going to be in 2's complement, and 8 bits for a fractional portion of my number. And so this lets me represent a smaller range of numbers, but with greater precision. In some of the code that I wrote to test out signed lookup table implementations, I chose for some of my sign tables to store Q0.31 numbers, because the sign function only ever goes from -1 to 1. So that let me represent almost exactly that range with a pretty small difference between each point. And even on processors that have floating point accelerators, integer math is almost invariably just going to be faster. And so if I switch from floating point numbers to fixed point numbers, as long as the accuracy I'm okay with, I can kind of speed up my implementation that way. Additionally, there are two solutions that have nothing to do with lookup tables, but for the sake of completeness, I'll share them with you. One is maybe I approximate my sign function with a polynomial function. So you can see here some of the Taylor series expansions for some commonly needed functions. Additionally, I can look at some Chebyshev polynomials or Bessel functions, and I can use these implementations to approximate the function I care about. The neat thing about these implementations are that I can kind of manipulate how long I spend processing and how accurate I am by just sort of controlling how many of these terms I include in my approximation. Lastly, a technique that might be useful to me is called memoization. Memoization is the process of caching recently searched for values such that if they're ever accessed again, the function can kind of return those instead of having to recompute things. So for my sign lookup table, right, I might have a local array of sign values that I've previously looked for. And whenever we are trying to get the sign of a value, the first thing I do might be to just see if that value was recently computed by looking in my array. And if it was, just return that value instead of having to do the lookup again or recompute the sign function again. Now for the sign function, that's way overkill. But you can imagine that if there were a function that were, requesting data from a remote server, that network interaction might take a really long time. And so in those cases, what I can do is sort of cache the last value that I asked the server from, and the next time I need that value, instead of waiting for the server to reply with the same value, I can just reply with the value that I've sort of saved in my little internal array. And so with all these different kind of implementation details, I've got a bunch of different knobs I can twist and levers I can pull to try to optimize my math function in a couple of different ways. Predominantly speed, how fast does the thing run, memory usage, and accuracy. And so if I want the most accuracy, I'm going with the library sign function. That's kind of the benchmark. But if I really want the fastest possible sign implementation, then what I might do is use a fixed point lookup table, which in my testing ran 64 times faster than the library sign. Now, a little caveat, this was using a set of tests called a micro benchmark, where I just sort of repeatedly called my lookup table and 1,000 times in a row and timed how long it took. In reality, my performance might not be quite as good if it's running on a system where I'm looking up a value, but then other processing happens in my application that pushes the lookup table out of a cache, and then on the next access to the signed lookup table, my system has to kind of load portions of the lookup table back into the L1 or L2 cache or something like that. And in my experimentation, the lookup table with the smallest memory size was a sparse lookup table. But like I said, with all the different things I can change with these implementations, it's kind of neat to me to think that I can pick any spot in this little triangle here and find an implementation that exactly balances the speed, memory usage, and accuracy that I need for my application. So you can see here some spots where where do the piecewise linear interpolation kind of versions sit? Where do my polynomial approximations sit? And of course, you can see in the table here, I can make my lookup table larger or smaller. I can move from floats to doubles to fixed points to try to find the just right implementation of sine for my application. Now, there's a lot of really neat applications of this idea of fast math that go way beyond just kind of like your standard math functions. So I can implement cyclic redundancy checks or portions of my encryption decryption by looking up a value from a table instead of trying to actually do some math. I think bit twiddling is a neat example, right? I don't have to write or test a piece of code to like compute how many ones are in a byte or whether a byte has even or odd parity. I can literally just make a 256 element lookup table, and whatever value goes in, I spit back out the right answer for the number of ones in that byte or the even odd parity. Charles Lora's got a couple of really neat examples too, where he is using lookup tables to kind of more or less spoof really complex signals that would be difficult to compute at runtime. So he's got a couple examples of sending out like data that can be displayed on a TV by sending out lookup table data, or even kind of spoofing zlib decompression by just indexing into an array and kind of sending that data out over some type of serial channel. Additionally, I think one neat application is direct digital synthesis, which is what allows us to create kind of arbitrary musical signals. So if I think of my sine lookup table as this kind of red line here, I could create a sine wave by stepping through this table at a specific rate and sending those data out to a speaker of some kind. And using the same array and actually stepping through at the same frequency, if I just change how many elements I skip over each time, then I can create frequencies, sine waves of almost an arbitrary set of frequencies. So in this case, if I kind of skip every other sample as I'm stepping through this array and wrapping back around, I can create from this one lookup table a sine wave at twice the frequency. And so here's an example using a sawtooth wave where I'm trying to create three different signals. So by adding three different elements each time as I step through my sawtooth wave, I can effectively create three different frequencies of sawtooth signals, add those values in software to create arbitrary musical signals, which I think is kind of cool. Okay, we've already talked about a fair bit of stuff. I want to pause to give you the chance to reflect. I've got a couple of challenge questions on here for you to reflect on. Number one, what are the benefits of encapsulating lookup table access in a function? Number two, can you list the advantages and disadvantages of putting a lookup table in Flash versus RAM? And lastly, can you think of a recent project you were on where having a lookup table to implement some kind of fast math would have been very useful? So I'd encourage you now to pause the video, consider these questions, and see if you can come up with an answer. If you're flipping through the lecture slides online, you'll see a couple of possible solutions in those slides before we move on. Okay, let's move on to our second benefit of lookup tables, which is helping us clean up conditionals. So let's say I've got a set of nested if statements here where I am trying to compute the insurance rate for an individual based on their gender, based on their smoking status, and based on their marital status. Here's one way I might do that, which is not awful, definitely fits on one slide, but as compared to a different implementation, there's kind of a lot going on. It's hard to make sure that this is doing exactly what I want it to do, at least for me. Another implementation might be this, where I'm sort of identifying the fact that a couple of these, combinations result in the same values, and so I can write the Boolean expressions that give me the correct insurance rate. But again, it's not 100% clear to me if if these Boolean expressions are correct, or if this conditional is giving me the right value. Here's what the lookup table implementation might look like. I'm creating a three-dimensional array based on the number of genders I'm trying to index, the number of smoking statuses and marital statuses, and now accessing the insurance rate for instance, a non-smoking married male is as simple as indexing into my array, and then at that location I get the value I'm looking for. What's neat to me about this is that I feel like it's much easier for me to look at this and kind of compare my notes and make sure that this lookup table or this set of conditionals, if you will, is giving me the right value based on my notes and design choices. This aspect of lookup tables is what Steve McConnell was describing when he said virtually anything you can select with logic statements, you can select with tables instead. In simple cases, logic statements are easier and more direct, but as the logic chain becomes more complex, tables become increasingly attractive. And we kind of saw a little example of that in the last couple of slides. I'll show you more as we move on. Now, at this point, you might be saying, well, sure, but not all of my conditionals operate on contiguous positive integers, right? Some of them are negative numbers, some of them are, floating point numbers. Sometimes they, want the same value for a range of data. So what do I do then? I've got a couple solutions for you, and we'll discuss each one. Firstly, if you just sort of are skipping over values, then maybe we only populate the array elements we care about. So in this example here, I do have contiguous positive integers. I just, I don't, the value 5 for whatever reason doesn't actually map to anything I care about. So maybe I just skip that value. Another alternative is to look up values in my table indirectly. So I'm going to have two lookup tables actually, one that contains the array indices that point into the second lookup table where I get my actual values. And you can see how I might use that here to get my input first to the first lookup table to get the correct array index, and then access the data that I need in my second array. This is most useful if I have an array of structs that are really large. So let's take a look at this example down here where I've got, let's say, a database of product information. And each struct that describes these products, let's say those are really large structs. If I want to reference those that array by a product ID, in this case, I might need to have an array which is as large as 2,304 elements. And if those structs are large, if they're 32 or 64 or 128 bytes, that's an enormous lookup table. I know that we are like sacrificing some memory for speed here, but that's a little wasteful even still. So one solution might be to make a lookup table with my product information, but just has those two elements. And then I indirectly access that through my first lookup table that contains the array indices 0 or 1 at the locations of the product IDs. And so in this case, I still have a 2,304 element lookup table, but each element's only an integer, as opposed to however large these product structs are. And that can be some memory savings. Additionally, by accessing this table indirectly, I can have another lookup table that gets me product information based on something like shelf location. So now if I type in, hey, what's at shelf location 56, the result that I get is index 1, and that gets me product B. So I can access potentially like a little database of information a couple of different ways. The third way that I might access my array if my inputs aren't necessarily contiguous positive integers is hashing. We've actually seen two examples of this so far. In the very first example of the lookup table, if the input is the array index, then that's actually called the trivial hash. But I can also set up a very simple expression, which we saw when we kind of modified that sign lookup table implementation. If I take my input, multiply by 64, round, then this is kind of a simple way to kind of permutate my input into the correct array index, or maybe I use the ternary operator to kind of find the correct value, the correct index into my array. Additionally, I could use an actual hash function. So here's an example of an implementation of the FNV hash, and this is super useful, particularly for strings or structs that I want to use to index into an array. So I can take like a word and compute the hash of that word, and use the hash value as the index into my array. If you are compiling with GCC, inside your array brackets, you can actually put whole statements. So not just like mathematical expressions, but we can get a little crazy with putting like little chunks of code inside here. If there's something just a little more complicated we want to do to get our array index. And of course, if it's anything more complicated than this, we can just sort of encapsulate that into its own function where, hey, for some value, the function does all the complex stuff to find the correct array index. Lastly, if I've got my lookup table set up like these key value pairs, like a sparse lookup table, then I'll just need to search. If my array is unsorted, then I might need to do a linear search. But like you can see on the graph on the right, as I get more than, I don't know, probably about 50 elements or so, that gets really takes much longer than a binary search. So it would behoove me in that point to make sure my my lookup table is sorted and then use the binary search to find the correct value that I need. Okay, let's pause again to practice some of the stuff we've just taken a look at. I would challenge you to consider how you might convert this set of if-else statements into a lookup table. Second, I've got another example that I really like because this would be a really hard example to do with implementation with if-elses, but it's actually really clean using a lookup table. So here's your second challenge, right? This is a situation where I've got some sensors monitoring my the engine status in my car, and I want to know kind of if I'm in any sort of danger condition based on whether my engine is in standard mode or turbo mode, based on the internal temperature of my car, the engine, and based on the RPMs that are my current RPMs. And so I challenge you, once you've tackled this first one, to then look at this second one and try to think about how you might implement this logic with the lookup table. I might even encourage you to take a stab at trying to implement this with if-elses, because I mean, you'd almost need a separate if-else statement for like each one of these blocks, which is, would be horrendous. But with a lookup table, you can write this in just a couple lines of code. All right. If you pull up the lecture slides, you'll see some examples of some solutions that I wrote, which I would encourage you to hold off on until you feel like you've got an example or a solution yourself. So take the opportunity now to pause the video and consider these two questions. And then when you are ready, unpause and we'll move on. Okay, so moving on to this idea of using lookup tables to simplify my conditionals. A really common design architecture that I'm going to encounter are finite state machines. So let's say I've got this finite state machine diagram here where I'm transitioning between these three states based on a couple of different inputs. Now, if I was going to program this, using kind of procedural code inside the function where I'm processing each event, then what I might have is kind of this gargantuan switch statement, right? I'm going to switch based on the event value that I'm looking at. So for each of my events, inside each of those case statements, I've got another switch statement based on my current state. And even if I've got a function to handle this, so like literally these are the case statements are no longer than this, that's still potentially a really long switch case statement to just handle my events. And I can clean this up significantly using a lookup table that we call a jump table. So what I'm going to create inside my function to process the event is a two-dimensional array of function pointers. And the array dimensions are based on the number of states and the number of events. And so it is as simple as looking up the function pointer at the array location where my current state and event are, and then calling that function. It's as simple as that to handle every event in my finite state machine. And you can imagine that even as this table gets relatively large, right, I can still fit that into like one screen. It's easy enough to see that and to make sure my finite state machine is set up correctly. Steve McConnell said, used under appropriate circumstances, table-driven code is simpler than complicated logic, easier to modify, and more efficient, which hopefully you've seen a couple examples of that, and we'll see more in the next couple of slides. Now, this idea of finite state machines kind of got me thinking, and Charles Lora's talk got me thinking. We can actually implement any sort of hardware we want on our microcontroller. And maybe this is a little backwards if you think about it, but the utility is that I don't necessarily need an FPGA to do FPGA-like things. So on the left-hand example here, I've got a simplified example of building a piece of sequential logic, another little state machine that's going to transition through these states based on the input A. And I can code this really simply using my lookup tables. And on the right-hand side, I've got an example of how I might implement like an actual piece of combinational logic in my on my microcontroller. And the lookup table in this case is literally the truth table for this piece of combinational logic. I can, if I feel like I need a piece of hardware external to my microcontroller, I can sometimes get away without needing that by simulating what that external IC would do in my microcontroller. It's what Charles Lohr caused him to say, sometimes when I thought I needed an FPGA, I've really been able to get by with just a software lookup table instead. Okay, let's take a look at our third benefit of lookup tables, which is the fact that it gives us some runtime configurability. So here's an example of a lookup table called system configs, in which I'm storing a couple of structs specifying an LED that I want to turn on or off. So in the first case, I'm going to turn on the LED at port A, pin 13. In the other case, port B, pin 6. And inside my code, now I can, let's say I'm going to read a little slide switch to control which configuration my system is in. I can access the correct kind of set of configuration information by accessing into my lookup table, and now the code down here that sets the LED doesn't care which LED has been selected, it just turns on the correct one based on my configuration information. I can even add a function pointer to this this set of configuration information, and so now I've got a system where searching is happening, but based on other data, maybe it's a slide switch, maybe it's whether or not my system is overloaded, I can control which function is used in each configuration for my system. If I'm printing something, I can use lookup tables to select which of several statements I want printed, and that starts to kind of look like my printf has polymorphic behavior. So in this example, I'm printing a floating point value, but if that value is above 2.1, then I'm sort of in the danger zone. If that value is between 2.1, and 1.45, I'm kind of in this warning zone, and otherwise everything's fine. And so by computing a couple of Boolean expressions on my floating point value, I can find the correct phrase that I want to have printed, and then my function call here prints different statements, all just based on the floating point value that I've got. Additionally, we can do stuff that looks like actual real polymorphism if I just include in my data type a parameter that specifies what type it is. So I can set up this like sort of overloaded function where I'm doing something with an abstract data type, and based on the type inside that struct, I can index into effectively a jump table to find the correct function pointer to operate on the piece of data that I've been given. And so here's an example of how that might look if, let's say, I wanted to kind of operate polymorphically on different types of loans. So let's say I've got a loan struct, and my loan can be either personal or business, and I want to update interest on each of these loans, but I want different functions called based on the loan type. So all I need to do is set up this lookup table here that correlates my type of my object with the function that I want called. And down here now, when I call update interest on whatever loan I've got, I will use that type to index into my array and call either update interest underscore personal or update interest underscore business to do the correct function on, the update interest function on whether this is a personal or business loan. Okay, let's talk about the last area where lookup tables give us this neat benefit that is kind of described as capturing our program knowledge as data. We've actually seen several examples of this already. For one, when I wrote my finite state machine as if it were a jump table, then I'm sort of encapturing in the table itself as data, as a set of function pointers, how I want my program to respond to each event inside each state. And what that means is that changing my finite state machine can be as simple as modifying my table. Adding a new input can be as simple as adding a little column in my table. If I want to change how a specific event is handled in a specific state, I can just change the function pointer at that element. And it makes modifying my program really simple. When we were looking at configuration settings, right? Adding functions or data or adding a new configuration setting for my system was as easy as editing or modifying my table. When I was looking at polymorphic data, adding a new loan type or adding a new overloaded function was again as easy as kind of just modifying some entries in my table, and that's really powerful because the business logic of the program in this case doesn't change. I'm updating and changing what my system can do by just editing the data on which it operates. I'll give you another example. Let's say I've got some buttons that I want my system to respond to, and in addition to doing something each time a button is pressed, let's say I want to specify a repeat rate. So if I hold a button down for a certain length of time, then it triggers the same action repeatedly. I took this example from this link here, so if you want, you can pull this up to kind of see the full source code. But in brief, I can easily implement this behavior with a lookup table that correlates my key being pressed, the button being pressed, with how long I need to wait for my repeat rate. And now in my code, all I need to do is check, hey, is this a new key being pressed, or has there been more time elapsed since we last ran than the repeat rate? In which case, in both cases, run the action that this button is associated with, and this is another great example of capturing what I want my program to do in the data. And so again, now if I want to add functionality to each of my buttons or change how long each one repeats for, it's as simple as kind of modifying my table or adding a little bit of logic to my code. Okay, let's pause here for another minute. And let me ask you, what feature do you think would be cool to add to this example of responding to buttons? And again, if you want, you can look up the full source code here in the article there. How might you implement that given this lookup table? And hopefully, as you're thinking through this, what you'll find is that adding information to the table or modifying what's here is much simpler than having to modify a bunch of procedural code based on each of these values. So I'd encourage you to pause the video again right now, think about this question, and then unpause when you're ready to continue. Okay, I've got two more examples of bundling together metadata in a lookup table that makes collecting the information together the same. If I've got a command line interface, many of us are familiar with the idea of, like, in an array, sort of matching the command line argument with the correct function to be called. If I've got a help string, then all of these elements here, by associating them in one array, one lookup table, right, I'm associating related metadata together. Another example might be if I'm writing a function that requires some user-provided parameter. Maybe I don't want the user to give me, a number or a string. Maybe I just want to restrict what they can provide. So I'm going to give them an enumeration that they have to give me to control what my function does. And then inside my module, right, I can have a lookup table that maps to each enumerated value all the information that I care about, right? The string representation, the RGB value, anything else associated with each color in this example. That's another example of, like, grouping metadata together. I've got one more example, which is using a lookup table to initialize peripherals on a microcontroller. And so in this example here, I've got a lookup table, an array of information about each timer that I can use to kind of iterate over and turn on or off each timer accordingly. So we'll say in this example, a very simple example, each element in my array lets me know, is the timer that we're talking about enabled or disabled? What's the base memory address for the set of registers that control that timer? What is the clock prescaler am I setting? What's the overflow value I want? And do I want to enable the ISR? So now what I can do is write one chunk of code that iterates over this array or this lookup table and turns each timer on and off accordingly. And that means that once I set this up, this chunk of code doesn't need to change at all. Anytime I want to change which timers are enabled or change the rate at which one he overflows, it's as simple as adding or taking away elements in my array or modifying an element in my table. Okay, so we've seen a number of really great uses of lookup tables. Everything from implementing fast math to cleaning up your conditionals to adding polymorphic behavior to capturing your program knowledge as data. So hopefully you picked up a cool technique while you were watching this video. I want to leave you with one more shower thought. And at the end of this presentation, I would encourage you to just sit back and think, where might a lookup table have improved a recent project you were working on? The shower thought I want to leave you with is, as I was getting these notes together, I realized that an array is one type of data structure, and it has these elements, where it's sort of fixed size collection of stuff. It can be sorted or unsorted. We're accessing it directly, essentially via some kind of index, and that mapped itself really well onto some unique solutions. As long as we were a little creative with what was stored in the array and how we were accessing that. And I had the thought, what other sorts of problems could we solve if we only had the right data structure? So let me leave you with one last example that I think is pretty cool. Let's say we wanted to write a command line interface parser, an interface to our microcontroller. Let's say where you had access to all the peripherals. So let's say this is some example of what we wanted our parser to be able to do. We can read and write from our GPIO pins and change the settings on that pin. I can read and write from devices on my I2C bus or change the settings on that I2C peripheral. And let's say that for this example, this is kind of the set of instructions that I wanted my parser to respond to, right? Initially, it'll get either an I2C argument or a GPIO to indicate which peripheral we're trying to control. And underneath each one of those, I can do different things. I can read and write from my peripherals, and I can change some optional settings in that in those peripherals. Let me ask you, how many lines of code do you think it would take to implement this command line interface parser? 100, 500, 1,000? It would take a lot to sort of get all of these, the nested if statements to make sure that these are all, I've got the right value in the right spot. This was intriguing to me because to me, this looks a lot like a couple of different data structures, and I'll share those with you in a second. But using those data structures, I was able to write this command line interface parser in 63 lines of code, of which 40 are really kind of the main engine that iterate over each of the arguments in our string, which are the 40 lines of code you see here. And so I want to share that with you to show you how I was able to take this really complex problem and map it onto a very straightforward solution. To start with, I'm going to exploit some regularities in the way we're structuring our input strings. So everything is of the format either argument or argument equals value. And I want my parser to be able to handle a couple of different situations. One where my arguments are either required, optional, or of this type called exactly one, where of all the arguments that are exactly one of them, but no more than one of them should be specified. And also I want values to be required, optional, or none if there's no associated value. Additionally, if I'm looking here at like my examples, right, let's look at the I2C example. If I give the read argument to my parser, I want it to know that what should be coming next are the device address to read from on the I2C bus and the register on that device to read from. But those arguments aren't required if what I'm doing is modifying the settings on my I2C device. So certain arguments will sort of queue other sets of arguments that my parser needs to look for to correctly handle each of these command strings. And so if I'm looking at this structure of all the arguments that I want my parser to be able to handle, what I start to notice is that there are two data structures in particular that this kind of looks like. Number one inside each of these chunks, right? Let's look at the top level. First thing I'm doing is looking for one of two arguments, either I2C or GPIO, to indicate which peripheral I'm trying to control. That I can think of as like an array of arguments that I'm expecting as the parser. And at each sort of stop in this collection of things I'm trying to respond to, I can consider all of them to just be an array, a lookup table, if you will, of arguments that I'm trying to match. Additionally, this really looks like a tree, right? Once I have identified either I2C or GPIO as my first argument, then I can sort of follow those nodes down into other collections of arguments that I'm trying to match in order to process my input stream correctly. And so I'm going to leverage both of these in order to write this code in a very simplified way. So if you think about it, right, each of these nodes kind of is essentially an array of arguments. So at the top level, I've got a 2-element array, one that specifies everything I need to process the I2C argument, one that specifies everything I need to process the GPIO argument. And so in order to do that, the elements in this array will include, one, the kind of string that I'm trying to match to say that this argument is present. And then, like we mentioned, that argument can either be required, optional, or exactly one. And it can have any required, optional, or no associated value. Additionally, in this struct, I'm gonna put a Boolean arggiven and valgiven data values to help me kind of keep track of when arguments and values are given, and those will be used later on essentially to do some error checking. Now, one sticking point is let's say I successfully write the parser and I've got all my data somewhere. How do I give that data to the function? If I want the parser to be function agnostic, then all of the functions that get called to handle these input arguments have to have the same function signature. And so my solution to that was to make all the functions take a single value, which was of type function params, which itself is a union of each of the structs that I might copy my information into in order to manipulate the GPIO peripheral or the I2C peripheral. And so in my argument struct, I've got offset values that describe where in the either the I2C or the GPIO struct to copy the information, and then I can pass that function params object into my function and have it reference the correct value. Lastly, some of my arguments, like in this case I2C, should trigger kind of like subsequent parsers. So the last element in my argument array is a pointer to the next subparser, if you will. So I2C, if that's been given, it should be expecting one of these arguments to come next, and so the parser will sort of fall into this new node in the tree, trying to match arguments into that array. And in some cases, once those arguments have all been specified, that node will point back up the tree so that the parser can kind of continue at a higher level. And so, just so you know, I'm not lying to you. These 40 lines of code work through each of those nodes in the tree. So the first thing we do is we get the next space-separated token out of our input string, and then we try to find that argument in the list of arguments that we are currently processing. And I chose to compute the hash of that input argument and use that as the index into my array to do this really quickly. It's essentially a single line of code. So once we've got our input argument, that points to a very specific location in the array. The next thing we do before we do any processing is make sure that we have a match. So hopefully, if we have an argument which is in the array, the hash points to the right location and we're good to go. If there's not an element there in the array, then it might be that I'm processing something higher up the tree. So in this little while loop, I sort of kind of keep moving up the tree until I'm able to match this argument with something in my arguments array, or until I get to the top of my tree, essentially. As long as I did find this argument, though, in my list of arguments, then I will copy into my function params struct any information that I need to know about the argument itself and about any value if one's provided. And then I am also going to update the parser. I'm going to move down the tree if that argument specifies like other parameters that I need to check for. In several locations, I'm going to check for errors, also just to make sure that like all of my required arguments and values were given. I didn't accidentally specify more than one of the exactly one arguments. And then lastly, I'm going to call my function, which again uses the hash to sort of really quickly in one line of code can find the right function to be called. And so if you go to this replit here, at this link, you can kind of see this in action and interact with this. I wrote a couple of stubs for the GPIO and I2C functions, so you can kind of read and write from arrays of dummy GPIO pins or dummy I2C devices. To me, this is pretty cool because there's a lot going on here, but this parser is much smaller than I would have expected it to be. And I think it's primarily because we found data structures to represent our data with that really closely matched what we were trying to get our code to do. Steve McConnell, in referencing lookup tables, says, sometimes it's not a good design just because we use inheritance or polymorphism, or even if we write really clean procedural code. Sometimes the key to a good design is a well thought out lookup table, or I think you could replace this with a well thought out data structure. To me, like a cool example, I wrote all this code here and kind of tested with the GPIO commands. And so once the logic, I liked it, I felt like it was working. Then I implemented all the I2C commands in this parser. And because the logic had already been kind of written and was good to go, and because all I needed to do to add these commands was add some elements to my tree. Adding the I2C commands, all of them here, plus the stub function that lets you kind of interact with some fake I2C devices, took me like 30 or 40 minutes. That was it, which is like crazy. And what's more, if you want to add another one, right, the logic is not changing. We found a way to encapsulate what we want our program to do in a data structure, and that gives us a tremendous amount of flexibility in adding and modifying features in the future. So the real final slide I want to leave you with is not just, yes, we looked at a bunch of cool things we can do with arrays and lookup tables in your code. I also want to leave you with this shower thought, right, that these were neat applications of the array data structure, and I wonder what software that might seem impossible could you write if only you found the right data structure to represent that problem with, and kind of expanded your thoughts about, like we did today with our arrays, about what pieces of data, structs or function pointers could go into that data structure to give you a very clean solution to your problem. Okay. If you want to read more, Charles Lohr's talk was a really neat one, so you can find this on YouTube. I've mentioned Steve McConnell's book Code Complete several times. Chapter 18 is all about lookup tables, essentially. And I've got a GitHub right here where I'm starting to post some of these examples. So if you want to see some of this code actually like more fully, bookmark that repo. I'll be adding to it over the next couple of weeks to kind of bring it up to parity with what was in this presentation. But that's all I have. If you've made it this far, I genuinely thank you for your attention. I hope you learned something and you had a good time, and I really hope you enjoy the rest of the conference.